Kruskals algorithm is a minimum spanning tree algorithm which finds an edge of the least possible weight that connects every two nodes in the graph. But there is only one way from node to every other node. There are no cycles, so this is a spanning tree and this is not, because we can get from B to D via E and we can get from B to D via C. It is greedy algorithm in graph theory. And what do you know about greedy algorithms? It takes the best choice. In this case, it takes edge with least weight and try to add this edge to a solution. If by adding this edge a cycle would be created, algorithm just move on to next smallest edge. If it can be added, algorithm just adds it to our solution. But there are two things that I didn't mention. First, how we decide that adding an edge will create cycle. And second, when we stop adding edges. Well, the second question is simpler, so let me start with that. If you have two nodes, you connect them by one edge, right? If you have three nodes, you need two edges to connect these together. And so on and so on. So for n nodes, you need n-1 edges to connect them. So in our example, we are adding edges until we have number of nodes minus 1 edges in our solution. Now, how do we decide that adding an edge will create cycle? We will do that by keeping track of every component, and if we want to add edge from A to B, we find out in which component they are. If these components are same, we cannot add this edge, because there is already path between these two nodes. But if they are in different components, we merge these components together and add this edge to our solution. Now, we need to figure out how to represent these components. We could choose two-dimensional array, but finding a set, in worst case, would take linear time complexity. So we use disjoint set structure. Disjoint set structure is a data structure that provides us search, creation, and union. When creating set, set's parent is set to itself, and rank is 0 because there are no childs. Well, a little bit of magic comes to play when you are trying to find in which set is some node. The findSet function returns the root of set, but on the second line we set the parent of x to the result of findSet of current parent x. What this does? Well, it makes the height of set smaller. It goes from initial node, but on its way to root, it sets every node as a direct child of root. So if we call findSet on D, function returns A as the result, but that set will look like this. And the last operation is union. This operation puts together two sets, and it does that by simply setting the root of a set with bigger rank as a parent to a root of smaller set. If they have same rank, the second one is set as parent and its rank is incremented. So if we call union on A and B, we get this. And if we call union on A and C, we will get this. Let me show you how this helps us with the Kruskals algorithm. As the pseudocode says, we create queue of sorted edges. Then we create disjoint set structure for every node in the graph. Then we are adding edges until their count is equal to number of nodes minus 1. So we take our first edge from B to C and check that B and C are in different components. They are, so we add this edge to our solution and call union on B and C. We continue with edge from E to D. Once again, we check that E and D are in different components. They are, so we add this edge to our solution and call union on E and D. Now, we take edge from A to C, and since they are in different components, we add this edge to our solution and call union on A and C. Now, we try to add edge from A to B. Since they are in same component, we cannot add this edge to our solution, so we move on to next edge. The smallest of remaining is edge from C to D. Since these nodes are in different components, we can add this edge and call union on these components. And by adding this edge, the count of edges in our solution is equal to number of nodes minus 1. So we are done, and we have found the minimum spanning tree of this graph.